Hi everyone, it's me, Clara. I'm back with another video on science. So I'm going to continue talking about superconductors, and I'm actually going to talk about the uses of superconductors. So in the last video, I talked about how because we can pass large currents through superconductors, we can generate these very large electric fields if we put our superconductor in a coil or in a solenoid shape, basically a sort of spring or a coil, and we can generate these really large magnetic fields, which is awesome. And so I showed you how we can use that to basically we can use them for particle acceleration, but we can also use it to create this large confining magnetic field for things like the Large Hadron Collider at CERN. We can confine the path using these very large magnetic fields in our superconducting coils to very clearly define where our particles are spinning, and then get them to basically boom, crash into each other at very precise points. So that's really cool. Obviously we don't make that many Large Hadron Colliders or so yes, we use a lot of superconductors when we do, and they're very expensive machines, but that's not something that we use all the time. And it's the same with tokamaks, which are fusion energy, which I'll talk about in the next video. These are very big machines that use superconductors. We use a lot of superconductors in them, but we don't make them all that often, right? So what do we use superconductors for on a more regular basis? Well, as it turns out, we use them for MRI scanners. So that's magnetic resonance imaging. So these are things that they have in hospitals. They're large tubes that you lie on a bed and you go inside them, and they can image the inside of your body, basically, depending on what they're looking at. And so this is the largest commercial use of superconductors. A lot of superconductors are sold for this purpose. So that's really cool. So I'm gonna just sort of talk a little bit about how we do MRI, what it is and how it works. A very basic overview, but yeah, it's kind of cool. I think it's super interesting. Now, before I go on, I will say that I hope you enjoyed my chat with Dr. Andrew Princep last week. I thought it was really fun, and I just had a blast. And it's really important to me to show that scientists, we are very, very different people, and that there isn't such thing as this is what a scientist looks like. I think most children, when they're asked what a scientist looks like, they draw Einstein, but that's not the case. Scientists we're all very different. Some of them even have tattoos, so I think that's really important. I'll be doing more of those talks. I've got a few filmed. I might change the order because there's a cool video series coming up. There's a new YouTube channel called Tigers in STEM. That's the inclusion group for equity and research in STEM. I'm part of that group, and we're going to be putting on a series of YouTube videos, webinars with different physicists towards the end of the summer. And so I might and one of the chats we talk about that, I have Dr. Izzy Jessahinger back, and we talk about those videos. So I might bring that one forward just so that it's before the event. I'll put a link down below. And also, as usual, don't forget to subscribe and like and stuff like that, because it really helps. Anyway, let's get on to the science of MRIs. So what's going on? So we're using our superconductors in MRIs. So I pulled an image of an MRI from the NHS webpage, which is the British healthcare system at the moment. So it's basically this big circular ring. You lie on a bed, it moves you inside the ring, makes a lot of noise. It's pretty freaky, and if you're like me, I've been in a lot of them and I get a little bit claustrophobic in there. But there's nothing that can be done about that. But I'm going to explain how we use these to get images of the inside of our body. Like I say, it's a basic overview. But the main ring, the big outer ring, that's going to be a big old electromagnet. And generally, these are superconductors. These are what we use, like I say, what we sell most superconductors for. So that is a big old superconducting electromagnet. What's cool about that is that when we, when they're installed, they're plugged in. You apply the voltage, the current starts to circulate, but then we've got this persistent current thing, which means you can unplug it, close the circuit, unplug it, and the persistent current, the current carries on traveling around the circuit. So that electromagnet doesn't need to be plugged in during normal operation as long as you keep it cold. The current carried on spinning around and producing an electromagnetic field. That's wicked, right? So I think that's cool. You only need to plug them in when you're installing them, or when you've been doing repair or something. So wicked. Then you have these gradient coils. I'm not going to talk about these gradient coils too much, but these are sort of how we decide where we're looking at the body. Like I say, I'm not going to get into that, but that's how we decide what bit we're looking at. I'm going to look at it very much higher level than that, though. And then we have RF coils, and you'll see why we have those things in there as we go in, because I will talk about that. It's kind of important to the story, if I'm honest. Let's take a person. So this is Clara. Clara is rock climbing, and Clara might have a fall and end up in an MRI. Might have happened, might not have done. Who knows? Anyway, the human body is actually made up of an awful lot of water, and it's actually made up of a lot of hydrogen. Got all these hydrogen atoms in us. Loads of them. Loads and loads of them. So our body is made up of loads of hydrogen atoms. More than the sort of 10 that you got on screen, I should point out. And we talked about hydrogen atoms. They're pretty cool because it's just a single proton in the nucleus and then an electron. We talked about that in the last video, or touched on it at least. But it's interesting. These materials, they actually have a slight magnetic moment. So these things, they have this magnetic moment. They actually spin. They have this spin. And so we can I've used an arrow to sort of show you the direction of the spin. It's spinning around, and that is the direction of the magnetic moment, which is being produced by this atom spinning. I'm not going to get into why, but this is something that's happening. So it's spinning on its axis. So we can just sort of say we've got this hydrogen atom, and then we've got this direction of the spin, say. And so in a magnetic material, all these spins line up and you've got a magnetic field. So why aren't humans magnetic? Well, maybe I have a magnetic personality, but maybe I don't. And that is because all the hydrogen spins are all random. They're all pointing in different directions. So they're all sort of cancelling each other out, right? Okay. So, like I say, Clara might fall off. And Clara might need to have an MRI. Put your arms down, Clara. There you go. Right. So we've got our MRI, and Clara gets put into the this big cylinder, basically. And like I say, the big outside electromagnetic superconducting coils are you basically got this big old superconducting coil that you're on the inside of, and so we have this magnetic field which we looked at in the last video. So we've got a direction of the magnetic field, and we can control the strength of that. And it's very uniform as well. This is really important. It's quite uniform. And so what happens is that in the body we've got this magnetic field, and then we've got our human with all the hydrogens, and these hydrogens are all spinning in different directions. They've got this magnetic moment spinning in different directions. In the magnetic field, they all line up, and they either go towards the feet or the head. Most of them will go in the same direction. They'll line up with the magnetic field, but some will, buck the trend, go figure. There's always one, right? Or in this case, lots. So we have these magnetic spins. They all end up lining up and spinning in a particular direction. And then we introduce an RF wave, and we point this in particular places. And what happens is that this RF, the energy is absorbed by the hydrogen atoms. And so what happens is that the spin, because they've got this extra energy, they're kind of pushed, and they spin in a different way. Basically, the way that they were spinning, the way they want to spin, which is in line with the magnetic field, changes. And then when we remove that, the RF, then over time that energy is released back as it returns to the position that it wants to spin in. And we can measure that. That's what's happening. And I'm going to talk about that spin a little bit more detail just to show you what's really going on. So let's take our hydrogen atom again. Let's make our beautiful 3D model. So now it's spinning. You notice I've changed the axis a little bit, spinning around depending on what that magnetic field is. And like I say, there's loads of them. There's loads of these fields. So they're all spinning. And they're all spinning out of phase. They're all spinning at different angles. They're all spinning at different things. But what we can do is we can introduce this RF pulse. Now this pulse, we pulse it at a very particular frequency. So we've got this Lamar frequency. We pulse them at a very particular energy, and what we see is that the atoms start to move in phase. So this is what we're doing with our RF. We're starting to force them to spin all together. I'm actually going to go over this video again because I think it's kind of cool. So they're all spinning out of phase, they're all spinning, and then we introduce and we start pulsing this RF frequency. The energy is getting absorbed and it causes them to spin in phase. You know, resonant frequencies, we're working at the resonant frequency. So if you've ever seen those videos of a bridge which happens to have all people walking at a particular frequency, so it starts to vibrate, the bridge actually starts to wobble. If you've not seen those videos, definitely look at resonance of bridges on YouTube because it's quite amazing to see. But yeah, if you apply a particular frequency, then things will start to move in phase. And that's what we have here. Our hydrogen atoms are all spinning now in phase. But they don't want to. That's not where they want to be. And the other thing that might happen is some of them might spin. Yes, that's right. Some of them might actually spin. They might actually flip. So instead of being in one particular direction, they're in the anti-direction. And actually quite a few of them flip. But that's not the position they want to be in. That's not where they're happy. They're doing that because we're making them by giving it this energy. So what happens when we remove this energy? Well, they've got all this. They basically want to return to the state that they were in. Okay, so the ones that were flipped want to try and remove back. And when it does that, it will release some energy. And then, like I say, these are all spinning and spinning, but as they spin, they don't want to be all in phase. They want to be out of phase. They want to be far apart. They want to spin at their own, where they're happiest, at their lowest energy state. So what will happen is that slowly over time they'll move out of phase. They'll start spinning at their own frequency, or rather, not at their own frequency, but at their own, in their own particular directions. And what's happening with this is as they're sort of choosing their own orbit, then they're releasing energy. So each of these is releasing a bit of energy. And what's really, I'd say, interesting is that depending on whether it's fat or water or bone, the amount of energy that will be released is different. The time that it takes to release this energy is different. So if we've got the hydrogen which is in fat and the hydrogen that's in water, we can tell the difference by measuring the energy coming off them. All these different energies, like I say, we know what they are, and so you can then have a computer monitoring when this energy is being released and how much is being released, and you can say this is exactly what this is, and you can build up an image of that. And so that's what we're doing with MRIs, basically. I think it's really cool. I really do. And then, of course, you come out of the MRI, and the hydrogen atoms, the direction that they're spinning returns to the rest state, the state, so they end up all random. They're no longer in one particular direction. So yeah, that's basically what happens with MRIs. We have a whole bunch of hydrogen, they're all spinning, they have this magnetic moment spin. We put them in, use the electromagnetic superconductor to line up the spins. Then we use RF to push them so that they're spinning at a different angle or a different rotational angle than they necessarily want to be at. And then we remove that energy. We remove the RF, and energy is released as they gradually return to spinning the circular angle that they want to spin at, and also in the right direction, because like I say, we actually cause some of them to spin upside down. And that is what we do. How cool is that? I think that's really cool. Like I said, it's a really simple version, but it sort of gives the basics of what's going on. And so yeah, the next time you fall off a rock face and you're in one of these things to see what you've done to your back or your knee or whatever, your skull. Yeah, I might have had my skull checked once or twice. Not sure what that says about me. Anyway, yeah, so I think that's pretty cool. That's what's going on. Of course, there's different things going on as well. You can introduce sort of like dyes and stuff like that can be absorbed, and like I say, you can check by using those gradient magnets. You decide where you're looking at, so you can look at slices of the body and stuff. But that's a very basic overview, and I think it's cool. So yeah, so that's what's going on basically. So thanks for watching. Thanks for sticking with me. So next week I'll put out another science chat video, and in between I'll do another rant video as usual, my Clara chats one, but a non-science video. And I am actually releasing videos on the Dice Tower board game breakfast as well. If you're a board game fan, I've sort of been on the board game breakfast, which is like the magazine program, for the last 3 or 4 weeks now, and I've already put in my next submission, so that's pretty cool. It's nice to talk about nerdy stuff. I talk about activism and stuff a lot all my life, and then I talk about science a lot, and it is kind of nice to talk about other stuff. I'm actually hoping that we'll start doing some music stuff as well on another channel that I'm working on with a friend, a dear friend of mine, whose birthday it was yesterday. Happy birthday, Tony. So yeah, I'll probably give a shout out. And yeah, I think I'm actually going to do something a little bit different for my sort of Monday, Tuesday video. I think I'm going to do a reacts video to trans TikToks maybe. I think that would be kind of fun. So, because they do tend to give me the feels. Yeah, so like I say, thanks so much for watching. It'd be great if you could like and subscribe. And until I see you next time, take care. Have a lovely weekend, and I'll see you soon. Bye bye.